All right. Good evening, everybody. It's just about 6:30. Welcome. Good evening, good morning, wherever you may be. This is the Science of Sailing webinar, sponsored by Navionics. So I'm Jenna Ferrieri. I'm one of the sailing specialists for Navionics. When I'm not working for them, I am a naval architect and hydrodynamicist for one of the firms here in California. And I also teach sailing part-time for J-World Performance Sailing. Just give me 1 second. I'm trying to figure out how to actually show my face. Which I'm not sure is possible right now. Okay, so we had a pretty good registration. We had just shy of 600 people, and it looks like we have a decent bulk of the turnout tonight. I do apologize if there was any confusion on the time zone. And then also if you signed in early, we all got bumped off for some reason. So hopefully you've all made it back over onto this one. And then just before we begin, I just want to go over the technology a little bit. So if you've never used the webinar software before, you'll notice that you have a dashboard on the right side of your screen. If it went away, just press that red arrow. It'll come back out. I have you all muted, so it's not because I don't love you. It's just so that it cuts down on the background noise, so everybody can hear me. And then the most important thing on this dashboard is down at the bottom. There's kind of an instant message chat window. If at any point you have a question, feel free to raise your hand or just type your question in there and we'll try to field it. I have the Western Regional Sales Manager for Navionics, Tashambe Moore, on the line with me so he can field and answer questions that I miss. And then anything that's beyond his sailing knowledge, we'll just hold off until the end and I'll try to answer it then. Okay, and if everybody's ready, I suppose we could begin. So the goals of this webinar tonight, just to put it all out there up front, is to understand how lift is generated from a wing or a foil section in flow, and then apply that to sailing directly, and then try to learn how the combined effects of those forces create the forward motion that we see and not just the boat kind of sliding sideways through the water. We'll then stem from there and go on to the telltales, how to judge how well your sail is trimmed, and then we'll kind of change gears a little bit and go into boat balance, talk about the center of effort and center of lateral resistance, and how if those are out of line, you drive an imbalance and you'll end up with weather helm or lee helm. And then the last bullet I have here is the main goal is to provide the foundation that you guys can hopefully use to improve your sail trim and your understanding of the sail controls. But the main point is that we're not going to be going that far tonight. So if there is interest, please let me know and I'll put something together for a second webinar, a follow-up. And I believe in the email you receive after this webinar, probably tomorrow, there's a short survey, so it asks about any other topics. If you think a sail trim, sail control webinar would be useful. Anything you think, if there's enough interest, I'll put something together for you guys. Okay. So hopefully, just trying to judge everyone's delay. So the outline, first we'll go through theory. We'll go through the Bernoulli Effect, the big myth that probably you have all heard, and then we'll go through just lift and drag in its basic form, and then we'll apply all of that to sailing. So we'll go through the modes of sailing, the foils on the boat that generate lift, and then how those work together to make that forward motion that we all know and love. And then we'll shift into telltales, and then finally shift into boat balance, where we'll talk about center of effort and center of lateral resistance. Okay, so theory. And first I'm going to throw a poll at you guys, just because we have such a large audience. It's nice to know kind of the level that I'm talking to. So this poll is just asking kind of your comfort level with sailing physics and sailing science. So I'll leave this open for a little bit. Okay, we're just about 80% in. Almost there. A few more people maybe. Give it a few seconds and then I'll close it out. Alright, so I'm going to close this out. So it looks like about half you guys know it, find it confusing, the other half know it and understand it, and then kind of some outliers, never sailed, learning. 1% are fluid dynamicists, so that's cool. Alright, so we'll come back into this now. Everybody's on the same page now, it looks like it. Okay. Back up one. Alright, so we'll jump right into the Bernoulli effect. So simple definition of Bernoulli effect is as flow is restricted, the particles or the fluid is going to accelerate through that. So think of it like the end of a hose. So as you put your thumb over the end of the hose, normally it'll just jump out, but as you put your thumb over it, it accelerates and it'll shoot a lot farther. So you're restricting that cross-section, but the same volume of fluid needs to pass through, so it must accelerate to go through. So the simplified equation, there are a few more terms in there, a few more variables, but in the simplified form, the Bernoulli equation is a pressure term plus a velocity squared term is equal to a constant. Okay, so pressure plus velocity squared is equal to a constant. So if one of those terms changes, so if pressure goes up, the velocity has to go down in order to maintain that constant, and vice versa. If pressure goes down, velocity has to go up to maintain that constant number. So the last bullet there is just the imbalance of pressure along a streamline, which we'll get into, causes accelerations and decelerations, because as you change velocity, you either have to speed up or slow down. So you're either accelerating or decelerating. So hopefully everybody buys that. And we'll move on to the myth. So we know from the previous slide that as you restrict flow, it needs to accelerate to move the same volume through, right? So applying that to a sail, you'll hear a lot of times, and I've heard Olympic level sailors say this, that the fluid accelerates over the top part or the curved leeward side of the sail, say, because it has to travel a farther distance and then meet up at the trailing edge or the back of the sail at the same time as the particle that goes over the windward edge. So they think because it's going that longer distance, it has to go faster to meet up at the same time. That is a myth. So, let's see if I can get some highlighters. So, the fluid particles don't necessarily have to meet up at the trailing edge. So as you can see in this picture at the bottom of the screen here, we've got, this was from a wind tunnel study where they just pulsed smoke through. So you can see you have the particles that went over the top of the foil, and you can faintly see the foil here. Let's see how well I can trace it. So the particles that went over the top of the foil did indeed accelerate, and they made it to the trailing edge before those particles that went over the bottom of the foil. So they didn't meet up at the same time, but they did accelerate, right? So the reason for that, the reason they don't have to meet up, is that those air particles, it's not, when it hits the leading edge or the front of the foil, it's not like splitting in half and going around and then has to meet up. That's not what's happening. So think of the air particles that go by, or fluid particles, it could be water, as, say, your friend and yourself walking down the street and you encounter a sign on the sidewalk, and one of you is going to go around one way, the other one goes around the other, but you don't necessarily have to meet on the back side of that sign. So that's exactly the scenario that we run into with the fluid particles. The other benefit, or the other, not benefit, but the other reasoning, if you still don't believe me, is if you think about the sail, you just have a fabric in the wind, in the fluid, and if you think about it, the distance on one side of the sail is virtually the same as the distance on the other one. So the leeward side, that distance around is the same as the distance on the windward side if you follow the sail directly. So we know from sailing that we're generating lift, but the distances are virtually the same. So right there, that kind of disproves that theory. So we know that it's not the distance traveled that's causing it to accelerate. So what is it? And it comes down to the pressure forces, really. So the first bullet I have there is the Coanda effect keeps the streamlines along the foil. So I suppose now I'll explain what streamlines are. So if you follow the path of a fluid particle along its kind of the field of view, you end up with a streamline. So like this line right here is a streamline. All of these lines are different streamlines. So different paths for each particle, say. So the Coanda effect is just saying that the streamlines kind of hug the foil shape. And again, foil's a little bit faint here, but it's right in here. So the term Coanda effect is not necessarily important, but a real-world application that you'll see every day is if you slowly pour water out of a glass or out of a kettle, and it kind of drips around the side, that's kind of an extreme case of the Coanda effect where the water is just clinging around that curve. So hopefully that gives you something to kind of compare it to. Basically, we get the accelerated flow and the pressure difference because of the curvature of these lines. So if you think of a particle moving in a circle, you get that centripetal force. So this is kind of going back to high school physics or college physics. So you have that centripetal force, and we know from that the inside of the curve is going to have lower pressure than the outside of the curve. So I'll just draw an extreme case. So if we have a curve here, we're going to get a lower pressure inside than we do outside of that curve. Think of that like a tornado or a whirlpool. So things get sucked into the middle of a whirlpool or in the middle of a tornado because there's lower pressure internal. So if you think of that curvature around the tornado or around the whirlpool, there's lower pressure inside of that curvature. And then in the grand scheme of things, we end up with pressure differences between the two sides of the foil. So that's going to generate lift for us. And the bigger the differential, the more lift you generate. But let's try to look at it a little bit more. So I'll explain it here, and then the next slide goes into a little bit more. But we know if we start up here and we travel down toward the foil, each of these streamlines that we cross, they're all kind of curved with that shape. So each one we cross, we're going to jump into a lower pressure and a lower pressure and a lower pressure, lower pressure, lower pressure until we hit the foil, and then we know that the pressure down here is lower than the pressure that we had up here. So we know that this is going to be the low pressure side of the foil. So that's my L. Now if we go to the other side and we start down here and we work inward, we can see that these curves kind of take that shape there. So we know that on the outside of that curve we're going to have higher pressure and the inside is going to be lower pressure. So each time we step across a streamline, we're increasing our pressure and increasing until we hit the foil. So we know this is going to be our high pressure side. Okay, so hopefully everyone is buying into this so far. So let's go through one more example just to make sure everybody's on board. So this case is air. So this is again that wind tunnel test, but they put in persistent smoke so you get the nice streamlines down. And again, the foil is kind of right in the middle here. So we know it's air, so we're going to assume atmospheric pressure along the top and bottom boundaries of this picture. So at some point the air is going to be undisturbed, and I'm going to take that as the boundaries of this picture. So we know up here we're going to have atmospheric pressure, and up here and down here we'll have atmospheric pressure as well. So we'll start at the top, and we're going to cross down through all the streamlines. Every time we make the jump, we decrease our pressure. So that's a negative sign. And then again, we'll decrease pressure, decrease pressure, decrease, 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 until we hit the foil. So we know that the pressure down here, because we've decreased with each of these jumps, we know we've dropped below atmospheric pressure, which is what we had up here. So we know on this side of the foil, we are at low pressure. If we start at the other end and work inward, again, a little bit harder to see on this, but these kind of take that curvature shape if you exaggerate it. So stepping in, we know atmospheric pressure, make an A for atmospheric pressure. Every time we step in, we're increasing our pressure because we're going to the outside of that curvature. So there's my plus sign. It's not very good. There we go, plus sign in a circle. So every time we make this jump, we're increasing pressure, increasing, 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 until we hit the foil. And then that's going to be a higher pressure here than we saw down on the outside. So we know this is the high pressure side. Okay. Hopefully everyone's buying into this so far. So now let's look at lift and drag in their simplified form. So what is lift? So we know we've introduced some shape to the flow that creates curvature to the streamline, so it makes them bend around it. And that bending creates a pressure difference between the two sides of the foil. So one side is going to be high pressure, one side is going to be low pressure. And lift is the component of the force that's generated that acts perpendicular to the flow and points in the direction of the low pressure side. So in this picture here at the bottom, imagine that these streamlines came in and curved around like this. We know that there's low pressure there, high pressure there, and then even lower pressure here. So the pressure just keeps decreasing as you go down. So we know that this edge is going to be our low pressure edge, so the lift is in the direction of that. You may have heard the term drag before. Drag is the component of that total force that's going to act parallel to the flow direction. And drag is simply a resistance force, and it slows you down. So if you think of trying to push a wall into the wind versus pushing a screen, the wall is going to have more resistance, more drag than a screen will. And then it's just pointing in line with the flow direction. So imagine either the foil is still and the flow is moving in the direction I have the arrow, or the foil, this gray shape, is moving that way, so the drag is opposite the foil motion. Okay, so we have our, vertical component and our horizontal component in this case, which are the lift and the drag. So if we put those arrows head to tail, so again back to kind of high school physics, put them head to tail, and then draw that missing component, which is this pink total force arrow, we'll get the direction that that total force is. And note that these arrows are not to scale in any way, so this is just an example, but basically, if you can reduce drag, you'll note that the total force now rotates and will point more vertical. So your total force is now being converted more into a lift force than kind of that rotated back force. And then the converse of that is if we have terrible drag and that arrow increases in size, because it's all scalar, so if that drag arrow increases, let's see if I can draw it. Say it comes out to here, our total force vector will now be in this direction. So you can see as you increase drag, that total force starts to rotate back. So that's not ideal. So in the ideal scenario, we reduce our drag and make that total force more in line with our lift. Okay. So hopefully everyone has followed along so far. And now we'll apply everything we just talked about to sailing specifically. So two modes of sailing that we'll talk about is push mode and pull mode. So push mode, you won't see more than just this one slide here, but push mode only occurs in the downwind sailing, and basically it's the wind just pushing against your sail and your sail is acting like a wall. So when you're sailing downwind, you just want to make your sail as big as possible, get as much area in way of the wind so that it can push against it. When you're sailing downwind, you don't really have an apparent wind. Since they're both in line, they kind of cancel each other out. So you're not really generating lift per se, minimal amounts maybe, so it's mostly just the wind pushing against it. And the best scenario I like to give is just put your hand out the car window and put it so your thumb is pointed straight up in the air, and the wind is kind of coming perpendicular to it, so your hand's just acting like the sail, and you can tell that the wind from your car driving along is just pushing your hand back. But now we'll go into pull mode. Hopefully everyone can see this slide. Yep. Okay, so now we'll go into pull mode, which is going to be in your reaching and your upwind sailing. So now if you put your hand out the car window and instead of putting your thumb straight up, you kind of angled your hand a little bit, now you can feel that your hand wants to pull up. So lift is being generated, and that's what's happening in pull mode. So when you're reaching and when you're sailing upwind, you get flow over both sides of your sail, and you're going to generate lift from that pressure difference. So I have kind of the simplified drawing down here, and let's see if we can kind of relate it back to those earlier slides. So we have the wind is the blue arrow, and we have our streamlines, which exaggerated would kind of take this shape around the sail, right? So we know atmospheric pressure out here, so as we cross in, we increase pressure, and then as we cross in, we increase pressure again, so we know that that's the high pressure side. Make that an arrow. Okay. Coming in from this side, we know somewhere out here in the undisturbed air we're again at atmospheric pressure. So every time we cross a streamline, we know we're decreasing pressure because we're going into the inside of that curve. So every time we come in, we're decreasing our pressure, so we know that that's the low pressure side there. So if the wind's coming down and say this was our boat, this would be the windward side, and this would be the leeward side. So we would generate our lift toward the low pressure, toward the leeward side. We'll get into this a little bit more later, but I just wanted to put it all out there now. But the pressure difference between the two sides generates that lift force. So this is just a depiction of the points of sail, just to go over kind of where the two different modes are applicable. So the run is going to be where your push mode occurs. You're sailing downwind, make your sail as big as possible, get as much area in front of it, and then as you start to head upwind toward the broad reach, you kind of transition now into that pull mode as you start to generate that apparent wind. As that starts to increase, you're generating lift over your sails. So as you get into the reaches and then up into the close-hauled upwind sailing, you're going to be in the pull mode. Okay, so now we know push mode, pull mode, how lift is generated, but how does that make the boat go forward? So on an average sailboat, so nothing high performance or anything like that, we have our sails, our keel, and our rudder. So those are going to be the three main foils, and each of them is going to create their own lift and their own drag. And the goal is to convert the forces on all those foils into a forward motion. But how does that work? So we're mainly going to look at the sails and the keel, or your centerboard or daggerboard. The rudder, I'm going to treat just more as a trim tab, so direction adjustment and not necessarily generating lift to move the boat forward. But it does provide some of that, but not as significant. No. So the picture on this slide here, I'll just wait so everybody can see it. Okay. So this is kind of the compilation picture, so don't let it overwhelm you just yet. We're going to break it down and look at each component individually, but I just wanted to put it all up front. But basically what's happening when you're sailing is, yes, you have forward motion, but you also have this slight side slipping. So the boat's going to drift a little bit to leeward, and what's happening is because of that, you're ending up with asymmetric flow over your keel, which is allowing your keel to generate lift. So if it was straight line flow into the keel, you'd generate lift in both directions, and they kind of cancel each other out. So the fact that there is side slipping motion means that your keel is contributing to that forward motion of your boat. So we have keel lift, and then from the flow of the wind, apparent wind over their sails, you're generating lift from those, and then ultimately combined, we end up with a forward vector for our motion. So let's break it down and kind of talk through each one individually. So let's look at the keel forces first. So we have, get the highlighter here. So we have our forward motion, which is the intended path, and then that combined with our side slipping, again, back to high school physics, we put the arrows head to tail, and then we get our actual direction of motion. So slightly rotated to what we intend the path to be. So if this is our actual path, the flow of the water over the keel is 180 degrees to that. So that's this arrow here. So you can see that it's putting an asymmetric flow over the keel. It's not coming straight on. It's got some angle of attack to the keel. So we end up with our curvature streamlines that look like this, right? So now, again, back to the crossing the streamlines. I'll get out the pen now. So we know we're at some standard pressure out here. Let me make that an S. Standard pressure here. And every time we make the jump across the streamline, we're increasing pressure. So we know that this is the high pressure side. So we're crossing to the outside of that curvature. And then same thing over here. We have some standard water pressure, whatever depth we're at, say. Every time we cross one of these streamlines, now we're crossing to the inside of that curvature. So the pressure is going to decrease. So that is our low pressure side. So the keel develops high pressure side and a low pressure side, And we know that the lift force is going to be perpendicular to the flow and in the direction of the low pressure side. So that's where this red arrow for the keel lift comes from. As we introduce drag, I'm not showing it here, I didn't want to overcomplicate things, but basically the total force would just be rotated toward the stern a little bit more. But we're just going to deal with it as lift today, just to get the points across. Okay, so that's keel forces. So now let's look at the sail forces. So we have our true wind and our boat velocity in this case, and then in this box down on the right here we have kind of that vector plot, so we get our apparent wind angle. So it's slightly offset from the true wind because the boat velocity is factoring in. So think of that as you're riding your bike and you have that wind coming in front of you from whatever speed you're riding at. So the apparent wind in that case is straight on at your face, but if you introduce, say, a wind that's coming straight in from your right, those two, the wind and then the wind that you're feeling from the speed of the bike, are going to combine to produce an apparent wind that's 45 degrees off your right side. So it's kind of a simplified way to say what's going on here with this apparent wind. So it's the wind that you're feeling with the combined boat motion and the true wind. So apparent wind is what's flowing over the sail. And again, we'll beat this to death. We have our curvature lines, streamlines, and every time we cross in, we're increasing pressure because we are moving to the outside of that curvature. And then over here, every time we're moving toward the inside of that curve, so we get our low pressure there. So we generate a low pressure side and a high pressure side. And again, we know that lift is going to be about 90 degrees to the incoming flow, and it's going to be in the direction of the low pressure side, so that's where we get this arrow here. Okay. And again, I'm not showing the drag, but it would just mean, let's pull the pen out now, so a drag force would be kind of back like that, so it would mean the total force is just rotated a little bit farther back. But we're only going to deal with lift to keep things a little bit simplified today. Okay, so we know we have keel lift and we know we have sail lift, but we still don't know what that means in terms of getting a forward force that's going to move the boat in the direction we want to go. So if we take each of these forces and look at them individually, we'll note that they have some component in this direction and then some component in the direction that we want to go, because we want to go that way. It's a terrible arrow. There we go. So we want to go in that direction. So we see that the keel lift has a component in that direction. Again, these angles are slightly exaggerated just to make things seeable. So we've got sail lift, and then this would be the drag on the sail. The total force would be rotated back. So we have the components. We see that we have, again, some component in the direction of the force that we want. So if we look over at the box on the right, an easier way to do it is to, again, just put the arrows head to tail and then fill out the rest of that triangle with the green arrow here, so that's our force forward, and that's what's going to push the boat forward. So there's a lot of different theories that I've heard the last few years teaching. Some students come in and talk about the watermelon squeeze method for understanding. If that works for you, I hesitate to say go ahead and use it, but go ahead and use it. I don't personally like it because it assumes, basically for those that don't know, if you pinch a watermelon seed in between your index finger and your thumb, it's going to shoot out in one direction. So some people relate the lift forces in the direction that the boat goes with kind of that scenario. So picture the boat as a watermelon seed and squeeze it together. I don't like to use that scenario because I think it makes people assume that the forces are directly into each other and kind of the same magnitude, when really each force has a component in the direction that we want to travel, and it's the kind of the summation of those vectors that's giving us the forward force, not necessarily a compression of those two forces. So, I mean, if it works for you and you can describe it properly, go ahead and use it, but just know that there is a little bit of error sometimes when discussing that theory. Okay, so hopefully everybody's bought into everything so far. It makes sense. It's hard with the webinar to see confused faces and things, so I'm just going to keep moving ahead, and then if there are any questions, we can go back at the end. But shifting now into Telltales. So the question that usually comes up after I teach this lecture is, well, how do we know if we're generating the maximum amount of lift that we can out of the sails, and what's kind of the first step to judge that? And my answer is that we start by using the Telltales. So for those of you that don't know, the Telltales are going to be those little yarn bits or wool, could be ribbon maybe, and they're usually along the luff of the sail, and those will be in pairs, so that's these guys here. Or they'll be along the leech of your sail, which would be these guys here. So the ones that are in pairs are usually going to be a red-green, or red-black, red-blue. Generally red is going to be on your port side, green, whatever other color will be on your starboard side. Easy way to remember it is it matches up with your navigation lights. But what you want to do is you want these telltales to be flying straight back. So that's the ideal scenario, is if they're all flying straight back. Occasionally, with your leech telltales, you'll get maybe this guy and this guy kind of flicking to the leeward side of the sail, but mostly we want them flying straight back. And if they're flying straight back, that means we have nice, smooth, laminar flow over the sail. We're not creating any turbulence or anything, so we're on the course to proper trim in that scenario. So the next question that usually comes up is, well, what happens if one side or if the telltales aren't flying properly? What do we do? So the first thing to say is that if one or both of your telltales aren't flying, it means you have turbulent flow over your sail. So you're getting disrupted flow. It's not nice and smooth. It's not nice and laminar. So you need to adjust the trim. So you have two options when you're using telltales. You can either trim or you can steer. So let's set up the example where we're sailing on a port tack, say, and so that means that the red telltales, the red yarn, is going to be on the side of the sail closer to us, and the green is going to be on the far side of the sail, and we notice that the green ones aren't flying properly. So the two options are that we can trim to the telltales that aren't flying, so if the green ones aren't flying, they're on the far side of the sail, so we'll ease the sail out until they start to fly. Or maybe we know we're trimmed properly and we have a new helm and he's kind of steering all over the place. So let's say we don't want to change the trim. We want to leave that and just correct our heading. We'll steer away from those telltales. So if the green ones aren't flying, we'll want to head up a little bit. So it means that we're over-trimmed for the point of sail we're on for that scenario. And it's easier to look at pictures. So I've got this little graphic here. So boat 2 is sailing properly, trimmed properly in this condition. So we've got our red telltale and our green telltale are both flying back, and they're sailing along nicely in this kind of close hauled direction. We'll look at boat 1 now. So boat 1 we can see is pointed a little bit higher than boat 2, and their red telltale is not flying back. It's not flying properly. So what are their two options? They can trim or they can steer. So they can trim to that telltale. They can trim in the sail until that red telltale starts to fly. Or we can see that they're pinched up. They're pointed a little bit higher than boat 2, so they could bear away a little bit and get on the same heading as boat 2 if they didn't want to trim. So maybe they were pinching up to get around a mark or something, who knows. But then they can head back down after, and then that telltale will start to fly again. All right, so let's see who's following along. I call it a poll, but it's probably more like a quiz. But what can boat 3 do? So boat 3 is the one on the right, and we can see the green telltale is not flying, the red is. What can they do to get the telltale to fly properly? So this is a multiple answer, so you can choose more than one thing if you want to. Okay, we've got about half of you have voted so far. Three-quarters now. Wait a little bit longer, see if anybody else wants to answer. All right, so it looks like most of you have answered, and most of you kind of get the gist of what's going on. But the answer is, oops, sure everybody can see it. There we go. And looks like everybody can now see it. There might be a few stragglers that can't from the internet connection. But the options for boat 3, so if the green telltale is not flying, the option is to trim to that telltale that's not flying, so they could ease the sail out. So that was one answer. If they didn't want to change the trim, the other option is to steer. So you can see that boat 3 is pointed a little bit lower heading than boat 2. So if they wanted to just steer to correct it, they could head up a little bit and get on the same course as boat 2, and that would fix that telltale too. Okay, it looks like most of you kind of get the gist of what's going on. All right, so we're just going to keep trucking ahead. We're going to shift into boat balance now. So boat balance kind of serves two purposes. You can think of it in the fore and aft, so bow to stern direction. And that's mostly what we'll focus on tonight. So that's going to be more of the what induces weather helm and lee helm. Or you can think of boat balance in terms of the heeling moment. And we won't talk too much about that today since that's more dependent on your sail trim and your sail controls. But in either scenario, you have your center of effort and your center of lateral resistance. So the center of effort, or CE if you see it in pictures, it's going to be the focal point of the force generated by the sails. Your center of lateral resistance is going to be the focal point of the force that's going to end up on your keel. So you have those two areas, and if you think of them in a vertical plane, the center of effort is going to be somewhere in the middle of the sails, and the center of lateral resistance is going to be down underwater, so you can tell as you get that heeling moment, those two centers go out of line and the boat's out of balance that way, so that's the heel in the boat. But we're going to look at it in the fore and aft, so about a stern plane, in terms of how that affects your helm. So I've got the next slide here shows pictures, so bear with me for a second as I describe it. But basically, if your center of effort and center of lateral resistance are directly in line between the bow and stern, you'll get a neutral helm. So you could let go of the rudder, let go of your tiller, and the boat should more or less sail in a straight line. If your trim is slightly off, or maybe you've put up a much smaller jib or reefed your main or something to create an imbalance, if you move that center of effort forward of your center of lateral resistance, you're now putting more power into the jib with respect to the main, so the bow is going to want to drive down away from the wind, down to leeward, so that's where we get lee helm. The converse of that is if we move the center of effort aft, now we're putting more power into the main, less into the jib, so the boat's going to want to drive up into the wind, up to weather, so that's where we get weather helm. So I like to think of it like a seesaw, like the kid's toy at a playground. So in these pictures, we've got the yellow horizontal line is going to be kind of the seesaw bit, and then we'll use the center of lateral resistance as our pivoting point. So when we have a balanced boat, both the center of effort and center of lateral resistance fall right on top of each other. So if we let go of the tiller, the boat will keep going in a straight line. If we move the center of effort aft, so we power up the main, so it's moving towards the stern, we can see that, say if we put a weight on a seesaw there, this end is going to want to go up in the air. So the boat wants to head up into the wind, the bow wants to go up. So that's going to be our weather helm scenario. The converse of that is the lee helm scenario, so if we move the center of effort forward, say we put the weight toward the bow on this teeter-totter, this seesaw, we can see that that's going to push the bow side of this down. So the bow wants to head downwind, away from the wind, to leeward, so that's going to be lee helm. So again, I like pictures. So we've got three cases here. We'll look at the boat in the middle first. Pull out the pen. So in this case, they have boat sails trimmed nicely, the boat's balanced, sailing off in this direction. If they let go of the tiller, they should more or less keep going in that direction. So now we'll look at the boat to the left, so the weather helm boat. So we can see they have their main trimmed in, and their jib is luffing. They've let their jib all the way out. So we can see go to the highlighter. If this were our pivot point here, we can see we've moved the center of effort aft, so that's going to want the bow to drive up into the wind, so that's going to create our weather helm. And if we were steering this boat, we'd find that we have the tiller over towards us, kind of, to windward of center line, to try to keep the boat pointed in the direction we want to go. So if you find that you have the tiller up to windward, kind of up around your neck even sometimes in really bad cases, you can tell that you have your main a little bit overpowered than your jib, so you want to try to equalize that balance. Maybe take in your jib a little bit, crack your mainsail, drop your traveler a little bit, and try to balance that back out. So we'll go to the lee helm boat, so the boat all the way to the right now. So this is the opposite condition, where they've let their mainsail luff, and they keep their jib nice and trimmed. So if this were our pivot point, we can see now that we're putting all the center of effort up into the jib, which makes the boat want to turn down away from the wind, and that's going to give us our lee helm. So we'll find in this scenario that to keep the boat going in the straight line that we want, we're going to be putting the tiller over to the leeward side. So if you find that you're doing that a lot of times, take in the main a little bit or crack off your jib and rebalance that power. So the poll that I have here now for you guys is, have you sailed a boat rudderless? Whether it's for an emergency or just for fun or in a lesson. Okay, about half of you have submitted. We're at about 85%, but it looks like the majority of you have not ever sailed a boat rudderless, which is interesting, actually. So when I teach, I like to spend lighter air days, maybe an hour or two in the morning. We just tie the tiller off on centerline and have the students steer with the sail. So it's really good practice to really see what your trim is doing to affect the helm and affect kind of what's going on in the boat. So they find that if they over trim the jib and the boat starts to bear away, without the rudder, it's just going to keep going unless they fix that imbalance. So if you're brave enough and you're in clear water, maybe in early morning, not a lot of wind, give it a shot. Especially if you're a racer. So if you sail your boat in races quite often, I find it's really helpful for beginner racers to see, so the more rudder movement you make, the more drag you're going to create. Think of it as your rudder is just kind of a door in the water, so if you put it, as you rotate it, you're increasing that frontal area, so you're increasing the drag area from that rudder. So if you can reduce rudder movement, you reduce the drag, so you can accelerate faster and maintain that higher speed. So the way you reduce your rudder movement is by helping your sails, using your sails to help you turn. So pre-start, say, you could use your jib, maybe trim your jib on early to help you bear away, gain that speed before you head back up and cross the line. So you can use your sail trim to your advantage so you don't have to steer as much with the rudder. Okay, just wanted to throw that out there. Okay, so we're nearing the end now. I just wanted to throw in some other terms that you may have heard or may hear in the future. But are kind of branched toward the next step of the sail controls and sail trim. But I just wanted to throw them in here to make everybody kind of aware who wasn't. But angle of attack is a term you might hear, so that's, I think I may have even said it a few times tonight, but that's the angle between the wind and the sail, or the fluid and your foil. So for sail trim, if you have turbulent flow over the sail, that means your angle of attack is incorrect, and so you adjust that with your main sheet trim and your traveler especially, but you're just adjusting the angle of the sail with respect to the oncoming apparent wind. Twist, so on the mainsail or even on the jib, you can have twist in your sail, so that's going to be the curvature of the leech, or the difference in the angle of attack at the foot of the sail and at the head of the sail. So if you go to centerline and go under your boom and look up at your mainsail, if it's twisted open, it's going to curve out and kind of, you'll see that increased angle of attack as you go up. And then the last term I have here is draft. So draft is just the depth and location of that max camber, the deepest part of your sail. And just some notes here is deep sail is for power, flat sail is for speed. And generally, you'll want to lean toward a deeper sail in kind of the medium light air, as long as your crew can keep the boat flat. And then as the wind builds and you get overpowered, you start to flatten off. But that all transitions into kind of the sail trim area, so we'll cut it off there for tonight. And that's all I've got for you guys. And now I suppose there's probably a lot of questions. So let's see what we've got.
Hi, Jenna. Can you hear me?
I can hear you, Dushanbe.
So there's a couple of folks that had their hand raised from the beginning.
Okay.
And Sam was one of the first ones. So I don't know if we can go and unmute Sam to get his question. Actually, he's not. His hand is not raised anymore. There's a few people that have their hands raised, and then there are several questions that need to be answered. So I'll let you decide which way you want to go first.
We can start from the bottom and work down. I have no preference.
All right. So the first question from Shirley is, how does she adjust her sails to generate more lift?
Okay, so that is a whole nother topic in itself, a whole nother at least hour. But the simplified answer is, to maximize your lift, you want to go for proper trim. So you'll be using your Telltales to judge how well you're trimming and adjusting the angle of attack of your sail with respect to the wind. So that's definitely the short answer, but there's a lot more to it.
And then the next question we have is from Jack Corland. Can the underwater current greatly affect the keel lift? Should you pull up on the keel if the current is too strong?
So your current will have an effect. I wouldn't pull the keel up to counter that. I would say current's mostly going to have an effect on the drag on your total underwater surface. I guess it depends which way the current's going. So if you're running against current and pulling the keel up is going to reduce the distance underwater that the center of lateral resistance is. So that could hurt your healing moment and mean you'd have to depower. So that could be one con. If the current is with you, it's not really going to affect anything. It's most likely just going to push the boat along. You could, if you wanted to reduce drag, I guess it depends how far you could pull your keel up and how much drag your keel produces. But if the current was with you, like when you're sailing downwind, if you want to pull it up and just reduce that underwater surface area, that could be one thing. So there are a few different scenarios, and I think it kind of depends, but hopefully that answer makes sense for now.
All right. And we have a question from Steve Hodges. Are keel and sail lift forces balanced in any way? And do full and fin keel behave similarly in this model?
So any keel or daggerboard or centerboard is going to produce the same sort of lift that we've talked about tonight. Whether or not they balance each other is a little bit different. So that comes into the boat balance respect. So the force on the sail is going to be greater in most cases than the force on the keel. So that's where you get that healing moment induced. So the more vertical you can keep your rig, the more you're imparting the sail lift force to be kind of in plane with the direction you want to go rather than down at the water, say, because it is I showed everything in 2D, but it is a 3D phenomenon. So you really want to try to keep your boat at about like 5-10 degrees as a compromise between your underwater surface area, so the drag, and then a compromise between keeping your rig upright to make that lift kind of help you move forward rather than heel more and into the water. So the lift from the keel is not going to equal the lift from the sail. It's simply kind of the arrows that I showed, if they're scaled properly, you'll get the proper amount of forward force. If that sort of makes sense. It's easier with pictures and a whiteboard, so I apologize.
The next question was about Telltales, and the question came from Hamish.
Okay.
And he said, what about when the top Telltales are correct and the lower ones are breaking?
Okay, so if some of the Telltales are flying and some of them aren't, that is a sail shape issue. So if, say, I'm going to reverse what your question is. If, say, the top ones aren't flying properly but the bottom ones are, it can mean that you're twisted too far open or you've closed up the top of the sail. So for the jib, that would be adjusting the car position, most likely. On the mainsail, that's Vang and main sheet. And I think without pictures, that's probably the best answer I can give you. It's a sail shape thing, so you'd be using your sail controls to readjust the shape of your sail to get proper flow over the entire sail.
Okay. And this statement came from Scott Halpern.
Okay.
35 years since I've had a fluid dynamics course. As I remember, the Bernoulli equation is derived from conservation of energy, but it has always seemed like the sail lift was the result of conservation of momentum. Sail lift analogous to turbine bucket that can't spin.
Okay, that's interesting. So the Bernoulli effect is conservation of mass, conservation of energy, because you can't create or destroy that. So you're trying to move this same volume of a fluid through a smaller area. So that's where the acceleration comes in. What was the sail part of it? Sail lift analogous to a turbine bucket that can't spin. So it's, in terms of momentum, I think that would more apply to kind of going from a dead stop and accelerating the boat. So when you don't have the proper flow over the keel's going to stall, so you will get more side slipping until kind of you hit that critical point and the flow starts to develop over the keel, and then you start to develop the proper lift underwater in relation to your sails, and that'll move the boat forward. So I think that might be what you're getting at with the turbine not being able to spin itself. I'm interpreting that as something that needs kind of a motor driver to get it started going, maybe.
So the next question is from Dennis. And what makes the Telltales fly up?
Okay, so it's up or down. I know I've, again, heard a lot of misconceptions with this, that, you know, if the Telltales fly up, that means a certain thing, versus if they kind of just slump down. But in either case, if they're not flying straight back, it means you have improper flow over the sail. So that's when you're going to want to trim to adjust that. So if one Telltale, or if a set of Telltales, if all the red Telltales aren't flying, you're going to want to trim in your sail if you're on a port tack. Or trim out if it's the other side of the sail where they're not flying. So hopefully that answers that.
And a question from Stephen. Why do some boats sail faster with a moderate amount of heel angle?
Okay. So normally what we teach is about like 5 to 10 degrees of heel. And that really comes down to the underwater shape of the boat that you're sailing in. So if you have kind of a tubby boat, pardon my description, but something that's kind of big and clunky underwater, you're going to generate a lot of drag from all that underwater area. So maybe a little bit more heel will get less of that area out of the water and reduce your drag. But for most of the racing boats that I've been on around the buoys, usually about 10 degrees is what we shoot for. Some offshore boats will go for a little bit more, especially in a sea state, but it's all about the underwater area between the different boat shapes.
And I have a question from Ron. how much of the effect does keel design have on the boat's performance? For example, full keel versus fin keels versus shoal keels.
Okay, so it does have quite a bit of an influence. It mostly impacts in the design process what the rig is going to end up as on the boat. So like the longer the keel, if you have a bulb on the bottom, you're going to have more weight down low, so they could put a more powerful rig up top because there's not going to be that fear of capsizing the boat or overpowering the boat too much. Fin keels and swing keels and things like that. I guess mostly for shallow water, you can raise the keel up. For those of you that don't know those boats too well, but yeah, again, it just comes down to the weight of the keel in those scenarios in terms of what the rig can be up top. And then the other side of that, again, is then the foil shape. So performance boats are probably going to have something like a NACA foil shape. Kind of the slower cruising boats might have a little bit more of a blunt shape since they're not going for speed. So the more pointed you have your leading edge, or the thinner or not as long you have your foil, the easier it's going to be to stall. So a lot of cruising boats will have a much bigger area just to make it more comfortable and easier to steer. So there's a few factors that kind of go into that, but they will all work in the same manner to produce that lift.
The next question is from Steve C. Can a large general such as a 150 move the center of effort aft enough as an effect to increase weather helm?
It certainly could. So a larger head sail alone could move it forward, depending on where the individual sail's center of effort is with respect to kind of the pivot point or the keel of the boat. So maybe if your rig is farther back, it might not have as much an effect as if your rig is a little bit farther forward. But certainly increasing the size of the sail, because that center of effort is going to be in the center of the area of the sail, so it will inherently move it back a little bit because the leash of that sail is farther back.
The next question is from Jack Corlin. What are the best materials for Telltales?
So mostly the cheap option is going to be just yarn. Depending on where you place them with respect to kind of the seams or the stitching on your sail, the yarn could fray, so they get stuck sometimes when they kind of loop up and they get stuck in the sewed seam. But that's certainly the cheap option. Ribbon, just normal ribbon, and make sure the ends don't fray is another option. But they're usually nothing terribly fancy, just simple.
The next question is from Gene. Could you say then that the more heeled over the boat is, the more sideways movement you're getting over the water?
So yes and no. The more heeled over you are, I'd like to think of it less as not optimum planes for your lift vectors. So if you think of it as a 3D, as you heel over, that lift force isn't converting as much to the forward. But in the case where you have like very far overpowered your boat, where maybe your sail is barely producing any lift because you're so far knocked over, so maybe in a broach scenario, pretty much everything is going to stall, and then you will start to side slip. So if you've ever rounded up or broached, you'll notice that you get large eddies off the keel as you're kind of stuck heeled over. So that's the scenario where pretty much everything is stalled. Your rig is too overpowered and the boat wants to keep forcing itself up into the wind, but the keel's kind of trying to fight you, but it's stalling. It makes all those eddies, so you're kind of like stuck in limbo until you depower your rig. I think it depends on the situation, but in certain situations, yes, it will start to push you more sideways as your keel loses kind of the proper flow over it.
Okay, so the next question is from Roland, and what about the slot between the sails?
Ooh, that's a big one. I'm going to defer that question to another presentation because I could talk for a long time on it. But as you close off that slot, so if you over trim your jib, say, you're going to affect the flow over the leeward side of the mainsail. So you're going to essentially decrease the lift by closing it off, so you can end up with stall points and stagnation points. And then if you open it up too much, you're just getting kind of the improper flow over both sides. So you really want to go for, if you look at the leach of the jib and then kind of the belly of the mainsail, you want them to more or less parallel each other as they go up and curve. And then if you're off from that significantly, you're going to be severely disrupting the flow over the mainsail. And I'll leave it at that because I can keep talking for a long time on those things.
A question from Roland is, we also get lift from hull and is shaped at different heel angles, or at least a statement anyway.
Mm-hmm. I would agree with that statement.
And Carlos was wondering whether or not the questions and answers will be available after the presentation. Carlos, the whole presentation, and your next question had to do with the full version of the presentation. The full version of the presentation will be available for everyone, so you will have the entire presentation available. Okay. And then, Jenna, the last question from Stephen is, what advice can you give ultra light and dead air speed conditions, puffs, sudden shifts?
Okay, so ultralight, so we're talking maybe 0 to 2 knots of wind would be my definition of that. So in ultralight air, it's a little bit against what you would normally go for light air sailing. So I had as my last bullet point, in light to medium air, you want to go for a deeper sail, more power. But in extremely light conditions, so maybe 0 to 2 knots, the flow over the sail is going to be so light that it's not actually going to be able to, that Kawanda effect I was talking about, it's not actually going to be able to cling to the sail with that kind of extreme curvature and slow speed. So it'll kind of shear off and then eddy and stall. So in extremely light wind, you want to go for the flat sail. So it's a little bit counterintuitive because normally you flatten to depower in heavy winds, but in very light air you want a pretty flat sail so that the air can cling to it and flow over it completely and not stall. Puffs was the next one, I think. So in a puff, depending on the boat and depending on how big the puff is, normally just an ease of the traveler is going to be your best bet. The way I like to explain it is you work really hard to get your mainsail shape proper, especially when you're sailing upwind and even racing. So when the puff comes, if you ease your mainsail, you're going to change the shape of it, whereas if you just ease your traveler down a few inches, you're just going to open up that angle of attack. And then once the puff passes, you can bring it back up and maintain that same mainsail shape. So that's my biggest advice for a puff. Aside from the sail shape, my comment on puffs, depending on the boat you're sailing on, make sure you have somebody looking out on the water so that you see the puff and prep for it before it hits you. So if it hits you and then you let out, you've reacted too late. So you really want to react to the puff before it hits you and knocks you over. And then, what was the last part? Sudden shifts. Okay. So sudden shifts. The tip I have for sudden shifts is, so I can talk a little bit more about this if you want, but when you're sailing, you want to make sure the shift is a proper shift and not a velocity header. So if you're sailing and the wind drops, it's going to feel like, because you're still carrying your momentum through, it's going to feel like, because your apparent wind has gone forward, that you're in a header, when in reality the boat just needs to readjust to the low wind speed. So the first thing to think about if you get a big header is to check your wind speed if you have instruments on board and see if it is a true header or if it's a velocity header. If it's a velocity header, kind of ride it out and then just get back in tune with kind of the lighter air condition, the lighter wind. If it's a true header, this kind of comes into tactics when you're racing, but if you tack so that you're then on the lift, generally you'll be sailing the shorter distance to the mark, so it's usually a good idea to tack on the header. The downside to tacking is that tacking slows you down, so there are pros and cons to it, but generally if you sail lifted to the mark, you're going to sail a less distance. So that would be my advice there.
Well, Jenna, we're a little bit over time now. There's one gentleman that had a question, and he's been patiently waiting with his hand raised.
Okay.
And then what I would say that if you still have questions, there's a couple of people that still have questions. Please send Jenna an email and ask the question, and she can field that question there. But what I'm going to do right now is try and get to the last thing with Sal and have him ask his question.
Okay.
And then we'll go ahead and end the presentation. So Sal, I'm about ready to unmute you, so go ahead and ask Jenna your question. Sal, are you there? Maybe Sal has stepped away from his computer. At any rate, I think it's a good time to end the presentation now. Jenna, thank you so much for a great presentation.
Yeah, thank you everyone for joining us tonight. And yeah, if you have any questions, if you think of anything later tonight or at any point, really feel free to send me an email and I'll try to get back to you as fast as possible.